Hello, everyone. Hope you're doing well. We are coming back now with some new material for us. Our first 2 weeks may have been a little bit of a review for us, although maybe not all of it was a complete review. Going back through the advanced calculus sequence with a kind of a bit of a brevity, as you might have noticed. Going through these things in just a couple of weeks means that there's a lot of stuff to kind of get through and wade through and try and remember and make connections with. But we went through and talked about a lot of important points that we're going to be really trying to hit home when it comes to this new world of metric spaces that we're going to be talking about today. This week, we're going to be looking at three big topics, which is spaces, convergence, and continuity. And we're going to take a day to just look at each of these different things to see what these worlds kind of look like when it comes to what spaces are and how they are different, what convergence looks like and how that's different, and then finally how continuity looks and how those things are different. We're going to have a couple of different pictures in each of these different directions for those of us who are picture people and understanding these from what these things look like in the space of Rm. In those spaces, we had a lot of neat properties that come from the real numbers or from vectors in the real numbers. And here we're going to be looking at how those might change if we're looking at the world of metric spaces. Now, metric spaces are an abstract thing, but before we get into talking about, okay, here's how we can be doing these theorems and things that work in all sorts of metric spaces, what I want us to do is to start looking at examples of metric spaces to understand why we can't just use many of the same sorts of topics that we were using from before. Right? Why can't we just use the fact that numbers are less than or greater than some of the properties that we're very used to in RM? We're going to see a lot of examples where things like that aren't quite possible. We've already seen maybe small examples and things that I've sketched along in sides of slides and stuff where maybe functions, you can say some functions are greater, some functions are less than, but there are many functions out there that do not have either of those two things happening. Some functions are greater than, less than, equal than, and potentially neither when comparing the two functions. So let's go ahead and take a look at some of these examples as we go through here. And as we're doing this, I want us to be looking at a few things. As we go through and look at each of these spaces, my encouragement to you is to be asking yourself a few of these questions. How is this space the same as RM? How is this space different? And then when proving this theorem that we're going through, are there any parts that become tricky or are now a little bit less straightforward now that our space is not R to the M? We'll see that a lot of the theorems that we want to prove are very similar to how we have the theorems that we've been talking about in the space of Rm. We're going to get through at some points things that look like the intermediate value theorem or the extreme value theorem, like we were talking about last week. And we're going to want to say, how did that proof differ now that we are in kind of like a different direction with this space that we're working on? Right? A generic metric space does not have a notion of less than or greater than. How many of our proofs relied on x values being smaller or greater? Right? So we'll see some of these things as we come about. We're not going to talk about functions on metric spaces right now, at least not until we get into continuity, into our very last moment here. Instead, what we just want us to be taking a look at these spaces, these values that are no longer Rm, but you'll see us just writing these metric spaces as capital X. Capital X just being some sort of space out there. Sometimes we'll be able to replace that capital X with some sort of very specific space, but in general, we're just going to say X is a space with a metric on it. Well, before we get into all of these sorts of notation things, why don't we go ahead and define what these terms are? We've already been teasing metric spaces for a while. Why don't we go ahead and say what a metric space is? In the definition below, think of the metric d, open parentheses, x comma y, close parentheses, as if it is the distance function, absolute value of x minus y, in the real number as real numbers. And check that this function satisfies all of these conditions. Here, the lowercase d is a function that plugs in two values from our metric space x. You plug in something from x in the x direction, and you plug in something from x in the y component there. And what you get out needs to be some sort of distance which is non-negative. So this makes a lot of sense in terms of d standing for distance. We really do want to think of the metric as a distance function. So let's make sure that this distance makes sense in terms of all the ways that we think distances should be. One, this distance function, and this is kind of an underrated part of this definition, this distance function cannot be negative, and it also cannot be infinite. You cannot take 2 points inside of this and gauge the distance between them and say, "Oh, that's infinity distance." That is not going to work for our metric spaces. We're going to ask that all pairs of points have a finite distance between them. You'll see that we have to sometimes make constraints on our spaces in order to make our functions have the semblance of distance, but that's going to become very important for us. For example, we might look at a space something like this. So here's like a non-example of a vector space because this one could have infinite distance. We might take the sequence of real numbers R, and we might look at the space of sequences of those real numbers. Remember, we've been calling that R infinity, something like this. So this is like the space of all sequences, x1, x2, so on and so forth, where here each x of I is a real number. And we might say, okay, well, let's say that I take two sequences, and in this class, we'll think about sequences x, which is really just x sub n, and y equals y sub n. If we are given these two sequences, then you might ask, John, is it possible for us to define a metric between the two sequences in the following way by just measuring the distances between each corresponding uh, point in each of those sequences, and then maybe just taking those and adding them together, something like this. This is the sum as n goes from 1 to infinity of the distances between x sub n and y sub n. Notice that this kind of looks a little bit like, a distance function when it comes to when you're looking in R2 or R3 and just kind of extending that to R infinity. The only difference is we're not taking squares of everything and then taking a square root on the outside. I've just decided to simplify that notation just a little bit for us here. But if we had something that looked like this, we could ask a similar question. Is it possible for us to take the notion of a distance formula in R2 and extend that a little bit to a distance function in R infinity? The difference with this sort of notation or the original notation that we had, which is just a bit simpler, the sum as n goes from infinity of x sub n minus y sub n, is that these two sequences might, when you sum them together, might give us an infinite value either within the square root or in terms of this infinite sum. Right, so for example, taking the sequence of just 1, 1, 1, and so on and so forth, and letting y just be the constant zero function, shows us that this could be infinite. With this as our example, either value could be infinite. So if we attempted to define these things as dxy for sequences x and y, then we wouldn't be able to actually say that this is a metric because the distances between these two sequences would be infinity at the starting point. So we get that these aren't really good notions of metrics for us because they can give us infinite values when we kind of try and measure what these two sequences are in terms of their distance. So that's going to be an important and underrated part of our metric spaces, is that all of our distances between two sequences needs to be finite. Continuing on here, distances need to have a few other things, right? We need to also be able to say that there is equality if and only if x is equal to y. So for example, let's say that you have two different points, x and y being two different points inside of our metric space. Well, it wouldn't make sense to say that the distance between 2 points that are separate, geometrically speaking, wouldn't make sense to say the distance between them is 0 because they're two different points. We want our distance function to separate points and say, if these 2 points are different points, then we want the distance between them to be non-zero. So another way to write this, and sometimes is a little bit more evocative, is that if x is not equal to y, we want that to imply that the distance between those 2 points is strictly greater than 0. So we already have dxy is greater than or equal to 0 from uh, our range, our codomain, for this distance function here. And so we just want to be able to say that the only time that you get that the distance function gives you 0 is if you're plugging in literally d open parentheses x comma x close parentheses. Our next thing says that the distance between x and y should be the distance between y and x, right? That's not something that is native to a function d. as a result, but we need to add that as an extra condition. This makes a lot of sense in our geometry. If we're taking the distance absolute value of x minus y, then that should be equal to the absolute value of y minus x whenever we're looking at these things in terms of r. So that's essentially what this one is saying. We should be able to say the distance between x minus y is the distance from y minus x. And that makes sense in terms of why we need absolute value to begin with. Then not only does it prevent us from getting negative values, it allows us to have a symmetric function, not relying on in what order we plug in x and y. And then finally, this notion of the triangle inequality is very important to us because it tells us that whenever you're going off in different dimensions of your space, you still are able to form triangles. That make a lot of sense to us. That having a notion of triangles allows us to build more complicated shapes in these spaces. So we just boil things down to the triangle inequality to say if we have multiple dimensions in our space, then they should work the way that we hope that they do. That is, that they satisfy the same triangle inequality that we were working with in the previous week. That is, that the distance between x and z needs to be less than or equal to the distance from x and y, plus the distance from y to z. Something that satisfies all these conditions is called a metric on the space x. And now a pairing of those two values together, a non-empty set x together with this metric d, that gives you what is called a metric space. A metric space can't just be the set x without the function. It is a set x, and it says, I'm going to give you not only the set x, but I'm also going to give you the function d. Those two things paired together is what gives you a metric space. Let's go ahead and take a look at some examples here. One says, the first example that I give here says that any arbitrary non-empty set can be a metric space. That means of any size of anything. That means you can just put any set that you would like in terms of x, and you can get a metric on that space. And that's using something called the discrete metric. The discrete metric is something like this, and this is something that I give to kind of break some of our intuition on what metric spaces can be, because you already may have in your head what distance looks like. Here is an example that kind of breaks some of that intuition. The discrete metric is this. Let's say that for any 2 points inside of our metric, let's say that the distance between those 2 points is 0 if x is equal to y, and 1 if x is not equal to y. That's it. This function can only take on the values 0 and 1. You can go through now and check the 3 conditions of a metric space. This is non-negative, and it has equality only if x is equal to y. It definitely satisfies that. It also is going to satisfy the symmetric property. And then finally, if you have any 3 points, x, y, and z, then you can go through and check that the distance between x and z is less than or equal to the distance between x and y, plus the distance between y and z. And that's because of the transitive property of equality. If you take the distance between x and z are not equal, right? If they are equal, then 0 is less than or equal to a sum of non-negative terms. So this one's easy to go through. Otherwise, if x is not equal to z, well, then you only have some options of what x, y, and z can be in relation to each other. The only thing that could break this inequality is if x is equal to y and y was equal to z, in which case both of these things would equal 0, and this would equal 1, and that would break this inequality. But that would contradict the fact that x was not equal to z to begin with. That's why I say that this relies on the transitive property of equality. If x is equal to y and y is equal to z, then it has to be the case that x is equal to z. That's something that holds true even in these just sets, because that's something that belongs to sets rather than to a particular space like R. So all told, this says that you can get this inequality straightforwardly. You actually get that this does work. This is the triangle inequality for this, and the 3 conditions of a metric are satisfied. Now, what makes this metric feel so weird is that it does not feel very continuous. You might say, okay, given 2 points in space, we know the distance between these 2 things, since these 2 points are not equal to each other, is 1. But you might start taking a look at 2 circles that kind of go around in a particular space, and then you might start just trying to move around in those particular realms there. Well, the issue is this. Let's say that you get to a point where you meander around and you have the 2 paths that you're taking in those 2 small circles around those points. Let's say that they meet. Well, then, if you're looking at the paths that you're taking as you're going around, the distance between any of these 2 points is 1, and then the distance between these 2 points is 1. But whenever you meet those 2 points together, the distance between the 2 points immediately jumps from 1 to 0. That's what I mean by saying it doesn't feel very continuous. Like, you could be moving and literally just be kind of an iota away from each other, and then suddenly you're back to the distance of 0. But remember that we're kind of breaking this picture apart entirely with metric spaces. The notion of far apart and close together is not defined by our geometric intuition in terms of this metric. It's defined by the metric. This says the only notion of being close together is being exactly equal. In fact, everything here is far apart. That's actually a little bit of intuition that's implied by the name discrete metric. It says that any 2 points that are not equal are actually, we should be visualizing them as far apart. If it helps, think of it as an actual metric space where everything that is not equal to the point that you're looking at is actually one distance away from that point. So if you're looking at this point, you're saying any point that's not equal to it is going to be a distance of 1 away from that point. That's exactly the way that we could be thinking about this, is that this is a discrete space. Now, it gets a little bit tricky because I know from my geometric intuition that that distance is not 1, and I know from my geometric intuition that that distance from this point to this point should not be 1. But that's exactly what this metric is trying to break inside of us, is that notion that the geometric intuition that we're getting from a lot of these other spaces isn't exactly the same as what we would be getting from the space that is induced by the discrete metric. Somehow, we are visualizing that any 2 points that are not the same have a distance of 1 away from each other in this space. So discrete metric helps us get there in terms of our intuition, but it doesn't take us the whole way. That's the jump that we have to start making in our minds and start stretching for these discrete spaces. Something that maybe gets us a little bit closer to our intuition, and indeed many of our spaces don't go as far as the discrete metric in terms of attempting to break intuition, are things like taxicab geometry. You may be familiar with this. This is a geometry that only allows us to move horizontally and vertically to traverse from point to point. For example, you might think that instead of us just being able to move on the XY plane in any particular direction, you can imagine a grid living on this space, something like this. And the only way that you can get from point A to point B is if you go through the roads, if you would, of this world, and be if you're able to take this and go from one place to another. So for example, the distance between these 2 points would not be 2 square root of 2. I'm assuming a kind of like that. These are the integers here. 1, 2, this is 1, 2. So I wouldn't be able to go from straight from 0, 0 to 2, 2 using a hypotenuse of a triangle and then take a do a Pythagorean theorem to figure out what that length is. Instead, I would have to travel the roads to get there. But notice that if I'm taking the shortest path, that there's multiple ways for me to get there, and that all of them have a length of 4. 1, 2, 3, and 4. So the distance between these 2 points is not 2 square root of 2. The distance between these 2 points is 4. So that would be a notion of taxicab geometry because it's how far a taxi has to take you to get there. Notice that the taxi cab is going to try and get you there in the fastest way possible so that you'll keep coming back and riding their taxi cab. So they are going to take the shortest length possible between any 2 points, and that's exactly how we can think of taxi cab geometry. So you can see here that the way that we define the metric is, if you have it in terms of R2, then you're just going to be defining this as the sum as I goes from 1 to 2 of the distance between xi minus yi, where here you're starting from the point x1, y1, or x, right? Actually, this is going to be from x1, x2 to the point y1, y2. So if this is x1, x2 over here, then this is the point y1, y2. Then the distance between those 2 points is given like this: xi minus yi in absolute value summed together to get us to that 2-dimensional space. You can imagine how this would work in a 3-dimensional space. You would just add the fact that now your taxi cab is now a space traveling taxi cab and can go up and down in terms of the space rather than just left and right in terms of the roads. It can now travel above and below you, in which case you can now consider the roads as being grid lined in terms of a 3-dimensional space. If it helps, you have this as your space. You have the grid lines on each and every strata that you'd be working on. So maybe here we have this, and then you have another grid line, and so on and so forth. And you also have a way to be able to connect to each and every spot here inside of our grid. So something like this. You're basically imagining like a checker box cube when you're able to travel this, but that cube is able to stretch out infinitely in every direction. And you can continue to think about this in terms of R4, R5, and any sort of dimension. The only way that you have to change your distance metric is like this. You're going to be summing over the difference between the changes in each and every dimension that you're going through in terms of the points. Now, there is one way that our metric, our pictures here are broken in terms of the intuition, which is this is very good if I want to go from a point with integer values to a point with integer values. But what happens if I want to travel right here, right in the middle of one of these squares? Well, a taxi cab is not going to drive through the buildings in this block in order to get you to this point. However, in mathematics, we are 100% fine to be able to go to this point. Here's how we're going to do it. We're just going to go halfway through this block, and then we're going to drive through all of the buildings that we have to go through in order to arrive at this point. So the distance between the point 0, 0 and this point, which we might call 1.5, 1.5, this point is going to have a distance 3 away from that point. Again, we can do that by just calculating this distance. So really, you have to imagine infinitely many grid lines, and the way that you're able to travel is only horizontally and vertically. If you're taking the shortest possible distance, it doesn't matter how you're going through and taking those lines, right? As long as you are just going right and up in some sort of discrete way, you're always going to be able to get there in terms of a distance of 3. Notice we're going to give a name to this metric because we'll see this one pop up as we go from place to place. We'll call this d sub 1. This is going to be a metric here where the powers of these absolute values are going to be 1. The reason for this is you saw back over here that we have some places where we do a similar thing, but we put a power of 2 in terms of x, the absolute value of x sub n minus y sub n. And that's kind of to emulate our distance formula, having these squared and then raised to the 1/2 power. That's actually going to be something called the d sub 2 metric. And we'll take a look at that one later as we come across it. And we'll call this the d sub 1 metric, or the 1 metric if we want to say that a little bit quickly. So hopefully this is good in helping us break our intuition in terms of how these are in geometry. And again, as a picture person, I want to be able to see pictures of these things so that I can have a solid foundation on what these metrics look like. Let's take a look at a metric that is very hard to visualize. Let's show that the distance between any two positive points, which is equal to the absolute value of 1 over x minus 1 over y, defines a metric going between just the positive numbers. This is going from 0 to infinity. So this is on R, but only the positive numbers here. Okay. So we want a metric between these things. Well, if we want to show that this is a metric, we just need to be able to show 3 things. One, is this distance always finite? We can think of this as our condition 0. Our condition 0 is dxy less than infinity. We can also ask if we want to, if that distance is always positive, or at least greater than or equal to 0. So that tells us that this is our condition 0 because we said that those distance functions need to be able to map into a codomain of the non-negative numbers. So let's see if we can show that that works. Given any two values, x and y, the absolute value of 1 over x minus 1 over y, perhaps we could go through and write what this is. If let's maybe start writing out what this looks like so we can start doing some things, although maybe even that sort of thing is not necessary. I think that I could figure out that this is going to be non-negative by just doing this. I notice that this is the absolute value between two numbers, and I can actually do this. I can use a triangle inequality here to make this the absolute value of 1 over x plus the absolute value of 1 over y. Now note that our x and y values are just positive numbers, so we can actually drop the absolute value here. So can we say that this is greater than or equal to 0? Yes, absolutely. Notice, first of all, that this is well defined. We haven't broken any of those rules because x and y are all greater than 0. So this is well defined. We know that this is greater than or equal to 0 since x and y are greater than 0. And we also know that 1 over x plus 1 over y is less than. And if we want to, we can do a little bit more math here just to convince ourselves of this. We could get common denominator and figure out what these things are. But at this point, I think we're also okay just saying that because x and y are finite numbers, 1 over x and 1 over y, these are finite numbers. One way to think of it is that the reciprocal function is defined on the positive numbers. And because of this, the sum of those are going to give us finite numbers, so we're good to go on our condition 0. What about condition 1? Condition 1 is, we've already got the positivity part, is do we have equality only if x is equal to y? So we need to check those two conditions. If x is equal to y, is dxy equal to 0? We do need that to be true. And the answer is yes, absolutely, because if x is equal to y, absolute value of 1 over x minus 1 over y is just the absolute value of 1 over x minus 1 over x. Everything here is well defined thanks to our domain for x, and so this is equal to 0. That's good to go. Then we also need to ask if dxy is equal to 0, is x equal to y? This is that if and only if. We need it to be true the opposite direction. Well, there's a few ways we can do this. We could maybe try and do this by contrapositive. We could start maybe by just saying, okay, take the absolute value of 1 over x minus 1 over y and equaling it to 0 and end up at this point. Or we could go through and say, let x be not equal to y. Then I'm going to show you that this distance is non-zero. However you'd like to do it. The two ways of solving these are about the same. So let's go through and see how we might do it. Well, if we want to say that this is equal to 0, maybe the first thing I could do is start by trying to get a common denominator here. I could also say, okay, well, this is either 1 over x minus 1 over y equals 0, or this is 1 over y minus 1 over x is equal to 0, and that in either case, 1 over x is equal to 1 over y. In which case, I know that the equality here tells me that x is equal to y after I do the equivalence relation that is guaranteed to us on rational numbers. So x is equal to y, and we are good to go. So that gives us 0 and 1. What about 2? 2 asks, is dxy equal to dyx? It absolutely is, and that's due to the fact that we have an absolute value. 1 over x minus 1 over y is equal to 1 over y minus 1 over x because of absolute value. So we've got 0 checked, we've got 1 checked, we've got 2's checked, and I've left all this space up here on the top for us to check condition 3. Because oftentimes the triangle inequality is the one that you want to take the most time with. Sometimes with things like this, it's a little bit tricky to think about how would I go about and show the triangle inequality for metrics like this. So remember what we want to do here is for condition 3, we want to ask, is d of xz less than or equal to dxy plus dyz. So we're going to get quite a few things happening here. So let's see if we can be careful with how we go about and work with this function. I'll pause the video real quick to make sure that I knew how to do it so that I wasn't going to explain it incorrectly. So let's go ahead and take the distance from x to z and write out what that is. But I'm going to write it in a way that gets me a common denominator. So the distance between x and z is going to be x minus z over xz after getting a common denominator between the two fractions here. And that's going to be, I'm asking, is this less than or equal to, well, I'm going to do the same thing here with the right-hand side. I should get x minus y over xy, and then x minus z, or rather y minus z over yz. Notice I'm keeping the absolute values there. That is important that I keep those absolute values intact there. Next thing I need to do is try and figure out how am I going to be able to compare these numbers. Right now, it's fraction compared to a fraction plus a fraction. Things seem to be a little bit easier if instead of trying to work with it this way, I instead try and work with everything that's not a fraction. I talk to this to my undergrads all the time. I am not a big fan of fractions, and maybe you are. But I try to get rid of fractions wherever I can. So I'm going to go through and multiply each term by the absolute value of x, y, z. When I do this, I'm going to get something that looks a little bit like this. Now all of my denominators should cancel since I've multiplied by my least common denominator. So I should be left with something like this after going through and multiplying. I'm just left with y after canceling the x and z. So I'm just to have xy minus yz. Note the absolute values stick around. And I'm asking, is this less than or equal to xz minus yz plus xy minus xz? Something like this. So I'm asking if these two things are an inequality. Do you see the next step? Now that I've written out what this is, do you see what the next thing is that is going on here? Maybe it would be helpful if I switched these two terms on the right-hand side around, but you might see that I have just added and subtracted the same term over here, xz, from something that already exists here on the left-hand side. So this is actually guaranteed. So this is by the triangle inequality for the distance metric, which is the absolute value function on R. So the triangle inequality here is automatic by the fact that I'm just using the absolute value function. So if I wanted to be very formal about it, I would probably say this is true by the triangle inequality for R, and then I would reverse each and every one of my steps to say, okay, well, that ended up getting me to this triangle inequality. But if you write something like this for your work, I totally understand what you're doing. So this works totally fine. So that's how we can go through and check the metric stuff. Notice that 3 maybe took us a little bit more thought. That is typical for these types of problems where you need to make sure the triangle inequality works. But now we know that these are the sorts of things that you have here. Something interesting to think about as you get to each of these metrics is now you can ask, what's true when what's different about this metric than what I would typically expect? For example, 1 over 5. What numbers are closer to 1 over 5 and what numbers are farther away is now an interesting question to ask. Well, notice that if I take something like 1 over a million, then that number is maybe around a distance of 1 over 5 from 1/5. But if I take a distance like 1 over 1, then that one's a distance of 4/5. I had changed my denominator by a little bit and I got a big difference, especially as I look to see how my distance goes, getting closer to my denominator is getting closer to 0. Whereas if I change my denominator by a lot, even if that change by a lot is having it go off toward infinity, then it may not be changing that distance all that much. So you can imagine numbers like 1 over 999,999 and 1 million are actually very, very close to each other in terms of this metric, or at least rather the numbers themselves. 999,999 and a million are much closer to themselves than, say, the numbers 1 and 2. So that's kind of the picture that we're getting. If it helps geometrically, maybe we're taking a look at the way that the numbers are stretched together on a number line is maybe they start at 0, then 1 has a good distance, then 2 has a close distance, then 3, 4, 5, 6, 7, so on and so forth. You're seeing that maybe as we keep going along, the distances for numbers get closer and closer to each other as we look over here at the positive integers. So it helps sometimes to be drawing pictures, getting an idea of what's going on in the metric that can help build intuition with some of these metrics. Now, given a metric space, we'll say that a metric is bounded if its diameter, that is the supremum of all possible metrics that you could get between any 2 points in the space, is finite. And this is actually possible because we can see here in this metric that a familiar metric on R can be shifted slightly to become a bounded metric. Notice that the numerator is just the typical metric on the real numbers, the absolute value between x and y. If I now take that metric and divide it by 1 plus the absolute value of x minus y. Notice the 1 plus there is important. That tells me that I'm not just dividing by the same thing in numerator and denominator and getting 1 for all of my metrics and undefined when x is equal to y. So this wouldn't even be a defined metric. The 1 plus says you're okay to be 0 when x is equal to y. And the way that you're going to be looking at this function is you're going to say if these 2 points are really far away, x and y, well, really, they're not that far away in terms of this metric, because if I have a number like 5 for this metric, then this is 1 plus 1 over 5. So I'm really looking at something that kind of comes across right here. Even if I'm looking at a million between these 2 points as the distance, then I'm looking at 1 million over 1 plus a million. So although that number is really, really close to 1, the way that my function, that is the kind of measuring this in terms of the distance of x minus y and the distance in terms of d, the way that I'm measuring this distance here is very, very relative. It's just kind of in terms of this. So if I look at this, then I notice that a way that I can measure this distance is I could say, okay, let's set this normal distance, absolute value of x minus y, to be a value of t. Then I can look at this function t over 1 plus t and start gauging what this looks like. It's bounded above by 1 when t is greater or equal to 0. And what we're plugging in are non-negative numbers. That's the normal distances. So this metric is bounded because the distance between any two numbers that I might try and use is going to be less than or equal to 1. This is a bounded metric. So again, you kind of get this picture here of the real numbers, but you're scrunching all numbers together so that the largest possible distance between any 2 points is 1. Our understanding of the number line is now extremely different, right? It's almost like there's a lot of number line on this side, and there's a little number line here, and then it continues to grow to be a huge number line on this side. But at the end of the day, I don't really have these arrows. This is a little finite little spot. So if it helps, this is 0, this is -1, this is 1, and then very close to here, you get 2, 3, 4. You get so many numbers very close to each other. So many numbers. And in fact, there's a little bit of a notion of, okay, well, what if I wanted to take a distance from 1 to -1? That is a distance of 2, and eventually you'll see that those numbers there, although it seems like they have to cross a great chasm, they're actually just kind of just going through it. So there's this notion of distance from 0 that works neatly from this, but really this is a picture of distance from any given number that you might plug in there. Distance from 5 to 4, for example, is a distance of just 1/2. So this is a very interesting picture, but even this picture doesn't quite encapsulate what this metric is attempting to do in terms of finding a distance. The utility of metric spaces comes from applying these to spaces of sequences and functions. Historically, where this stuff came from is in trying to solve partial differential equations, things like the heat equation, stuff like this. You may be familiar with the term Fourier series, depending on where you've been in your mathematical journeys. And a lot of this sort of of this math materialized with the question, where do Fourier series work? Are there particular types of functions for which these work? We also get sequences of functions based off of this. So we want to take a look of sequences as well and try and analyze what happens with spaces of sequences. We'll start with this before we get to spaces of functions and sequences of functions, which we'll eventually get to in the second unit of this class. But the intro to classical analysis part of this is saying, how did we develop this sort of analysis historically? Where did it come from? And at some point, again, in the latter half of this class, I'll bring up Fourier series and Fourier analysis a bit to say this is kind of where some of this stuff is going toward. This is what it was used for in a historical sense. So let's go ahead and take a look at how these metrics might work in terms of subsets of real sequences. We've already seen one, or at least a non-example of one. You could take the set of sequences of real numbers and start trying to apply the D1 metric to it. The issue is you get something that is infinite if you choose your two sequences accordingly. But let's say that we did something a little different. Let's take S to be the set of all sequences, X and equal to this, and let's take them to be all of these sequence values where the absolute value of each of the values inside of the sequence, all of the real numbers in the sequence, is less than or equal to 1. So this is a subset of R infinity. Then let's define the distance between any two sequences, x and y, to be the sum as n goes from 1 to infinity of 2 to the negative n times the absolute value of xn minus yn. Notice that this is a little bit of a difference between the D1 metric, right? I've applied a weight. We call this 2 to the negative n a weight, W-E-I-G-H-T, to each of the absolute values inside of this sequence. So the weight here, what it's doing is it's saying, okay, you really want to make a change. You mainly want differences in the first term of your sequence to be like pretty heavily recognized. But if there's a difference in the millionth term between the two sequences, oh, that's going to be just like that difference over 2 to the 1 million power. So it's not going to measure that much. Now notice that there's something interesting going on here, which is that let's say that you had two sequences that only differed in the millionth term. Like let's say you started with 1, 2, 3, 4, or rather you had a constant sequence of ones, and you had a constant sequence of zeros, except in the millionth term, you told them to switch, right? The constant sequence of ones becomes a 0 in the millionth term, and the constant sequence of zeros becomes a 1 in the millionth term. Well, then what's the difference between those two sequences? The distance here is going to be 1 over 2 to the million, but notice that that difference is non-zero, and that's something that's important to us in a metric. The distance between them is very, very close, but it's non-zero. That's going to allow us to still say that this is going to be a bounded metric on the set S. And there's going to be some interesting ways to kind of show that this thing works. Let's go ahead and take a look at the triangle inequality argument here, and I'll leave kind of the rest to you. So if we wanted to do a triangle inequality with this, what would we say? We want to show that the difference between x and z, here x and z are sequences, are less than or equal to the distance between x and y, plus the difference between y and z. The way I'm going to start this argument is I'm going to start by looking at the difference between any of the terms inside of this infinite sequences. So I'm going to start with the statement for all n. And maybe to be clear, it's for all n the natural numbers. Here I am saying let's let n be a natural number, one of our indices of this sequence. And I'm going to start by saying that this term in that infinite series, which is in this case 2 to the negative n, absolute value of x of n minus z to the n. I'm going to start by saying, just by the fact of triangle inequality for real numbers, that this is less than or equal to 2 to the n x sub n minus y sub n plus 2 to the negative n absolute value of y sub n minus z sub n. Notice that this is just true by the triangle inequality for real numbers, at least for, the absolute value function on real numbers when that is applied with that metric. I am taking the triangle inequality as is and just multiplying through by the number 2 to the negative n. Well, what do you think about what's going to happen if I take an infinite series now of sequences where this is less than or equal to this? Well, now I can just use the comparison test. So by the comparison test for series, because each and every term in my sequence is less than or equal to, I'm going to be able to say that this n equals 1 to infinity of 2 to the negative n times the absolute value of x of n minus z to n is less than or equal to the sum, as n goes from 1 to infinity, of the same thing. Notice here what I have, something like this. And that's true by the comparison test. Term by term in this infinite series, I have a less than or equal to relation. So in the infinite series, I'm going to get the same thing. The last thing that I can do is just say that this is equal to the sum of each individual term given here, because all of our terms are non-negative, it's okay for me to reorder these as needed. So I could just go through and sum these like this. Oops, not plus there, minus z sub n. And now I have the inequality that I'm looking for. That gives me exactly that, what d of xz is less than or equal to d of xy plus d of yz. So that gives me all that I need. So that is a neat way to show the triangle inequality for things like this. Is using things with infinite series usually means you're trying to apply some sort of comparison test. You'd like to do a term-by-term comparison of what will result from the triangle inequality. Looking at the nth term, this is what I end up getting, and then I'm going to sum over all possible n. Now, something else that's interesting here that I haven't defined is the fact that the metric is bounded. I want you to try and see if you can see why this is bounded. Note, you're going to need this condition here, and that's exactly what this hint is trying to say. Try replacing S with just a set of all real sequences. Is this a metric? Try thinking of if you can find, here's a little exercise, which is find sequences x sub n and y sub n in R infinity such that dxy is actually infinity, or goes to some sort of infinite value, right? So basically saying that this infinite series that is given in the dxy does not converge. So such that the infinite series in dxy diverges to infinity. So see if you can work to try and find what that looks like. It's a pretty interesting type of exercise to see if you can do that. Okay, so this gets us a little bit into some of how other ways of defining these distances and types of sequences are. It's a good thing we've talked about series because a lot of our metrics that are important to us have to do with sequences and functions. And in order for sequences and functions to be in order to apply a metric to these sorts of spaces, we need to be making infinitely many comparisons between all different terms inside of that sequence. Oftentimes, that means that we're taking a series. In terms of functions, we're going to see we oftentimes want to be taking integrals of these functions so that if there is a difference between any two functions, then that's picked up by the integral of the difference. In fact, here's an example of what I'm talking about. Let's define this space, which is the continuous functions going from A to B. So picture-wise, this is saying I'm just looking at the functions that are continuous going on an interval from A to B. So I might have functions that look like this right over here. And depending on what my A and B are, outside of that function, I might have discontinuity, like the function 1 over x. But if A and B are both positive for the function f of x equals 1 over x, then it's still a continuous function on its interval. So I could still say that 1 over x is inside of the continuous functions going from, say, 1 to 2. But I could not say that it is in the continuous functions going from 0 to 1, because the function 1 over x is not defined at x equals 0. Then we can define a few different metrics on the same space. We've already defined different metrics on the space of R, like the absolute value function or absolute value of 1 over x minus 1 over y, and we could do the same thing for the continuous functions. Notice that some of these involve the integral. We're going to define a metric, we'll call it d sub infinity here, between f and g to be the supremum of the absolute value of f of x minus g of x. This is a metric on the continuous functions going from a to b. To be clear here, this is the space of functions going from R to R, but what are our elements here that we are going to be taking our metrics in are not the values of R. The elements that we plug into this metric function, f and g, are themselves continuous functions, and they are getting plugged into the metric function. This is something that maybe we haven't seen. This is a function that plugs in functions. So we have to be very specific. F and G are our continuous functions going from A to B, and the metric function d sub infinity here. What this does is it says, okay, I'm going to take two of these continuous functions in there, and I'm going to give it a non-negative value. That is going to help me measure the distance between these two functions. So the way that I define d sub infinity is as the supremum of the absolute value of f of x minus g of x at any given point. So, for example, if I'm given a function like, let's say we're on C01, and I'm looking at the difference between f of x equals x and g of x equals x squared, then I am looking to see what is the possible maximum value that these two things can have, right? What is the possible maximum distance? So I'm looking at the supremum of the absolute value of x minus x squared for any x inside of the interval going from 0 to 1. So that is exactly how I'm defining this. So note here that this can be sometimes a little bit tricky to find. Here, I think that the best way that I could think of to do it is to look at the function f minus g and look for a maximum on that function. That would mean that I am looking for what? Taking its derivative, setting it equal to 0, and then saying, okay, at that point, x equals 1/2, where the derivative of that function is 0, I'm going to just try and figure out what that difference is, and that should be able to tell me what the maximum value is here. So in this case, that's going to be equal to the absolute value of 1/2 minus 1/2 squared, and that's going to give me 1/4. So the distance between these two functions in a function sense is 1/4. That tells me how this particular metric works with this space. Now notice that I'm saying that this is a metric. I haven't gone through and shown triangle inequality with each of those. And my encouragement to you is to try and use some of the properties that we've been talking about with suprema and things like this to try and show that this is a metric. That's an exercise for us, is to show that this particular d infinity is a metric. Also, I'm also claiming that this d infinity of f comma g is bounded. or rather, maybe I'm not saying that it's bounded. I'm actually trying to say that this is finite regardless of the functions f and g that you could plug in here. The reason, so the question we might ask is, why is d infinity of f and g always finite for all f and g in the continuous functions from a to b? The simple answer I'm going to try and give you here is the extreme value theorem. That the extreme value theorem tells us that this is always finite. That is, that the supremum that we're actually finding here as the difference between f and g, well, remember, f minus g is a continuous function if f and g are. And so finding the supremum of the absolute value of f minus g, that is just finding the maximum of this value, is something that you can attain on a closed and bounded interval, like the closed and bounded interval going from a to b. So the extreme value theorem is going to tell us that this distance is always finite. That's something that you need for a metric. So that's a little hint to kind of help you out there. Maybe these other functions are a little bit easier to determine if they are metrics because they use some of the properties that we know about integrals from Calc 1. The function d sub 1, plugging in f and g, which is the integral going from a to b of the absolute value of f of x minus g of x, this is a metric on c of ab. Here, the triangle inequality kind of follows directly from the triangle inequality for real numbers, plus the fact that integrals of a sum of functions is equal to the sum of the integrals of those functions. So as you're going through and showing that this is a metric, try using some different perspectives on that to show that this one's a metric. Maybe D2 is a little bit trickier than D1, but it kind of satisfies many of the same sorts of ways that you would show maybe that the Euclidean metric is a actual metric, that it satisfies these three inequalities, or these three properties of a metric. This is that d sub 2 that I have been elusively talking about. Notice that d sub 1 between f and g can be written as the integral from a to b of f of x minus g of x to the 1 power, and then all given to the power of 1 over 1. Whereas d sub 2 of f and g is the same sort of thing, but it kind of generalizes the Euclidean metric a little bit in the sense that the distance now between f and g is taken to be squared. And then after summing those things together, notice that I'm thinking of the integral as a kind of an infinite sum, that you take the square root of that value. So this gives you d1 and d2. So there's a lot of similarity between how these two functions are defined. So this is a lot like a generalization of the Euclidean metric between functions now instead of in between vectors or in between sequences. So my encouragement is to try and use some of the things that we've been working through with Suprema and other types of metrics to show that these things are actually metrics. Let's go ahead and get some more practice with finding actual distances between these functions. Let's take f sub n to be the piecewise function that is linear from negative 1 over n 0 to 0, 1, linear from 0, 1 to 1 over n 0 and 0 elsewhere. And let's find the distances between each of these functions. So drawing out what is given here, let's say that this right over here is negative 1 over n comma 0. This one right over here is 1 over n comma 0. And at this point right up here is 0 comma 1. So the rest of these are going to be given right over here. So here you can see that I've kind of defined these functions based on the value of n. So f sub n is itself just kind of a value that is reliant on the function of n. So I don't quite know what that value of n is here, and I'm not trying to solve for that. Instead, I am saying I want to take the distance between this function that I've drawn and the function that's just 0 everywhere. So let's get some practice in calculating what these distances are. Starting with d sub 1 f sub n comma 0, what I'm looking for here is this. I want to find the value of the integral going from, this case, these are functions that are defined everywhere. So this would be a function going from negative infinity to infinity of the function, which is basically this triangle, f sub n, absolute value, minus 0 dx. So let's see if that's something that we can find. Well, that's just going to be this area beneath the triangle, right? It's going to be this area that we have right over here. So instead of just trying to figure out what this is in terms of a function and trying to write out each of those parts, something that I could do instead is this. I could just say, okay, well, what is the area of the function underneath this triangle? Well, it's going to be 1/2 times base, and that base is 1 over n minus negative 1 over n times the height of it. And that's going to give me what? Something like 1 over n when I go through and multiply all of that. So this gives me that d sub 1 s sub n is 0 is equal to 1 over n. What about d sub 2 s sub n 0? This one's going to be a little bit trickier because now I need to be taking negative infinity to infinity. This time I need to be taking f sub n squared inside of here. Notice that minus 0 is going to be there as well, but I'm going ahead and taking that out since that's going to give me this. And that's going to be to the power of 1/2. So now I need to think about, okay, what are the pieces of this function? I need to be able to write this piecewise function so that I can square it, then take its integral, and then raise it to the 1/2 power. So maybe I need to try and figure out what this is. Well, I know that this is a line that connects negative 1 over n 0 to 0, 1. So I can go through and just do a little bit of a, what is it called? Point slope form to figure out what this is. So I think that the slope of this line is going to be n, and that it has a y-intercept of 1. So I believe what I'm going to end up getting here is something like this. We should get that this is the line y equals nx plus 1. And I can do the same thing here, this time with a slope of negative n and a y-intercept of 1. So connecting the line going from 0, 1 to 1 over n 0, that should give me y equals negative nx plus 1. So I know now how I'm going through and integrating this. So this one's going to require a little bit of calculation to get through and figure out what this is. But eventually we can get to the point where we integrate this and we get an actual value for it. So I'll let you kind of finish out to see what value we get for this distance. Notice that you're not going to get the value 1 over n for this value. The distance between these two functions is going to be different. The fact that you're squaring, integrating, and then taking it to the square root does not mean that you're going to get the same value here for whatever this distance is going to be. Let me compare this to the distance f sub n to 0. This one is surprisingly fun to find. You're just looking for the supremum of all possible values of the absolute value from f sub n and 0. And this is given any x value that we might be plugging into our function. This is for all x in the real numbers. But notice that this function is pretty much 0 everywhere except at this tiny little spike. And the farthest that this spike can get away from the function 0 is 1. So the distance, the infinity distance between f sub n and 0 is 1, whereas the d1 distance is 1 over n. Notice that each of these different metrics tell us something different about how we're viewing distance between these functions. We would say that this function right here is very close to the function 0 in the d1 metric. And in fact, the more that you scrunch everything together in terms of the values of n, the closer it is to 0, because the integral of the difference between those two functions gets to be very, very small as you continue to push n forward. However, regardless of the value of n, notice that the d infinity distance is 1, because the way that d infinity is getting measured is it's saying, don't worry about the integral, just give me the farthest away these 2 points could be. And because we're always at the point 0, 1 for this function, regardless of the value of n, we're always going to be 1 away from 0 at some point. So that supremum is going to be equal to 1. So notice that some of these formulas rely on n, some of them don't. And the way that these two things interplay is going to be very interesting for us moving forward. Here's another problem. I want us to take a look at some of these metrics on R2. Let's take a look at this. Let's take the distance between 2 points on R2. So I'm going to call them, kind of in contradiction to how I had called them before, x1, y1, and x2, y2, instead of doing x1, x2, and y1, y2. So this way, I'm thinking of them as maybe it's like xy coordinates, and it helps us make sense of some of these formulas over here, which look a lot like how we would write the distance formula for R2. So notice that this right here, that this is our D2 metric here for 1, and that's this number 2 right here, that this is going to be that's D infinity, and that this one over here is our D1 metric. How do I know that these are what these are? Well, D2 is going to be the square root of the sums of squares of the differences of these between these values. This d1 looks a lot like the sum as I goes from 1 to 2 of the values x of, or rather x of 2 minus x of 1, and then you could do the same thing for y sub 2 and y sub 1. Maybe a reason why I don't like using that notation. But these are just the sums of these things to the 1 power, so that looks like a d1 metric. And then this d infinity, only thing I've done different than the d infinity metric I defined up above in the previous slide is that I've placed a max instead of a supremum, because we're only really connecting a finite set of things to figure out if there's a max. So I don't really need supremum because the supremum and the max would be the same thing in this instance. So that gives me a d infinity metric. Let us draw the following set. The set of all values x vectors inside of R2 such that the distance between the x vector and the 0 vector is less than or equal to 1. With respect to each of these metrics. Let me actually draw a picture here before we get started, because we know what this unit ball is even if we haven't called it the unit ball before. This right here is sometimes called the unit circle. If I have that this is the value 1, 0, and this is the 0.01, then this is the unit circle here. This is called the unit circle because it satisfies the equation x squared minus y squared or plus y squared is equal to or is less than or equal to 1. Anything inside of this little unit ball, which is now how I'm going to call it, because it's not just the circle inside, but it's also the stuff inside when I color it in like this. This is called the unit ball in terms of our standard metric on R2. But what metric is that? Which one of these is the standard metric here? We can actually go through and figure this out. So if I'm looking to see, for example, for this first part, the distance between an arbitrary point x1, y1 and the point 0, which is given to me here in this formula, and I'm seeing where this is less than or equal to 1, then what I'm looking for is, I'm plugging things in here for the distance function. This is x sub 1 squared plus y sub 1 squared being less than or equal to 1. Notice I'm able to square both sides. X sub 1 squared plus y sub 1 squared is less than or equal to 1, and this is actually exactly this formula. This is the formula for the unit ball. So if I wanted to be specific about what kind of unit ball it is, this is actually the d sub 2 unit ball. This is our standard Euclidean metric on the real numbers. This is what we consider to be the unit ball or the unit circle shaded inside, because it gets us all of these values that are of distance 1 away from 0, where the distance that we're using is d2. So that's to kind of give us some intuition. How would this be different if I was given a different metric? What about the metric given here in the second bullet point? This is the distance between 2 points, x1, y1, and x2, y2, which is equal to the max of these two values. So I'm looking again to see what are the values if you take some value x1, y1, you give it to 0, 0, and say, where is that less than or equal to 1? Well, that's going to be what? Now it's going to be the max of x2 minus, well, this case is just going to be 0, x1, 0, and y1, 0 is less than or equal to 1. Well, if I need the absolute value of x1 and y1 to be less than or equal to 1, in order for this max to be less than or equal to 1, then I can just say, okay, well, both of these things just need to be less than or equal to 1. If either one is greater than 1, then the max is going to pick up on that and make it bigger. If I have anything, however, inside of this set where x sub 1 is less than or equal to 1, absolute value y sub 1 is less than or equal to 1, then this maximum has to be less than or equal to 1 by this condition. Writing out what this is really just taking x sub 1 and making it be in between -1 and 1, and y sub 1, this is having this be in between -1 and 1. So the picture here is that I get all of the values here between x sub 1, between -1 and 1, and I also get all of those corresponding y values. Notice that what I get when I trace all of that out, I get something that kind of looks like a unit square, don't I? So the picture here is I'm getting all of the values inside of this square. Notice the difference between our two pictures. The points that are a distance 1 away were a circle in the d2 metric, and they are a square in the d infinity metric. So there's actually more points that are kind of close by to things inside of the d infinity metric than they would be in the d2 metric, at least in this particular instance. I'm going to leave it to you to check that what you get out of 3 here, and the unit ball you're going to get for 3 is something that looks like a diamond. This is going to be all of the values that are sum of x1 and, or in this case, x1 and y1. So you can kind of see maybe why this is true, because if you now are just taking this as your formula and making the relationships with these to the 0.00, then what you're looking at is the absolute value of x2 plus the absolute value of y2. I guess we could be calling these x sub 1, y sub 1 is less than or equal to 1. Well, this is going to be the boundary of that where all of the sum of these is equal to 1, and that's going to be up on these diagonal lines. Things like -1/2, comma 1/2 are going to be in this line, and that's on that little diagonal line on the top left. So you can go through and check and make sure that that gets you this unit ball for this particular example. A few things that I want to talk about before we start ending out for today. Let's take a metric space and let's consider a restriction of a metric to a smaller set. Well, if you take a subset A of that metric space and you restrict the metric D to that subset of A, well, you're going to get a metric space in its own right. Think of this as like how remember in linear algebra, you could have a subspace, and typically that's something that's rather tricky. You have to check many conditions. But a submetric space is rather easy. You can just take any subset of the metric space X and just restrict the metric to now only exist and be defined on any points inside of that subset that you've defined. That gives you a metric space. Oftentimes, when we discuss a subset of a metric space with a known metric, we will not take care to redefine the metric because we know that we could just restrict the metric down to this subset. A way to show equivalence between sets in terms of their size is by using a bijection. But to show an equivalence between metric spaces, we often use an isometry rather than a bijection. This is going to be a special type of function between metric spaces. We're kind of getting started in talking about these functions between metric spaces, which is one of our main goals of defining metric spaces to begin with. Let's define what an isometry is before we discuss how it can be thought of as a bijection. Let's assume that x and y are metric spaces. Then an isometry is a bijection, so it is a bijection between x and y, but it satisfies the particular property that the distance between any 2 points in the domain is equal to the distance between where those 2 points in the domain are mapped in the range. Notice that the distances here, the distance functions, are given different like little indices. D sub x to say that this is the distance in the domain set. D sub y to say that this is the distance in the codomain set. So what we're saying is that this function not only needs to be a bijection, but anytime that you map 2 points through that function, that if these 2 points have some distance from each other, then they have the exact same distance from each other in wherever they are mapped. We will say that x and y are isometric if there exists an isometry between x and y in this way. So the reason for this isometric definition is the same as the reason behind showing 2 sets have the same cardinality. If there exists a bijection between 2 sets, well, then they have to have the same size. So an equivalence between sets in terms of size tells us, okay, at that point, we're just saying that there's a bijection between the 2 of them. Similarly, if there is an isometry between these 2 metrics, they share an even stronger equivalence. Not only do they have the same size, but they also have the same notion of distance. X and y are isometric. Means they share the same notion of distance. So this is the right way of connecting 2 different sets. If they're isometric, that means we can not only say, okay, these are basically the same set in terms of their size, we can also say these are basically the same space in terms of their distance. So we can do something a little stronger if we know that these 2 sets are isometric. Sometimes, however, asking for a bijection between our 2 sets is too strong of a requirement. So sometimes we just ask for a map that preserves the distance going from one set to another. In this case, we will have what is called an embedding of metric spaces. So here's our definition. Say x and y are metric spaces. We will say that it is an embedding if there is a map that takes d sub x, x of y to be d sub y to be going to exactly the same distances. Notice that the only thing that we've really left off is that this is not a bijective function. However, anything that is an embedding must be an injective function. And I want to give you this as an exercise to show that a map that has this property right here, show that this map must be an injection, that it cannot be 2 points mapping to the same point. Think about distances and how that connects for this particular exercise. So here's an example. Let's take our metric space and do the thing that we were talking about from before. Let's take a subset of that metric space and make it a metric space in its own right, using the exact same distance. Well, then you can just take that subset of the metric space and you can embed that back into the metric space itself. This has a natural embedding given by, well, just take the map that gives you I of A equals A. This is something that you can do uniquely in this case because A is a subset of X. You don't have to really change the element that you're mapping it to. You're just mapping it to be inside of X rather than inside of A. This notation here is different. This is the notation that we will use for an embedding. We don't use this one quite very much, but in case we ever see it, then this is a kind of a combination of two things. AD embedded inside of XD is kind of combining two different symbols. One is this symbol right here, that's the function symbol. And it's combining that with this symbol, which is the subset symbol. If you kind of think about what these two things are combined, you're saying that this function is defining that A is a subset of X, in this case, a subspace of X, a metric subspace, a space that is a subset that is a metric space, if I were to define that. So it's kind of combining those two notions together with this one function. It is a function that is defining this as an embedding. We have a quick proposition here that we're going to be needing in our future stuff. So I'll go ahead and define it real quick. You may have seen this in terms of the real numbers, but the inverse triangle inequality also holds in terms of metric spaces. I'll leave it to you to see that this actually ends up holding with this triangle inequality, because the proof here is very similar to the inverse triangle inequality that is given for us in terms of real numbers. If you're not familiar with this, then I recommend that you get some practice with this. The idea is, this context says, if we need to bound a difference between differences, where the two values inside of a distance are shared, then you can absolutely do that. In this case, you could say either dxz minus dxy is less than or equal to dyz, or you could say that because of the absolute value, dxy minus dxz is less than or equal to dyz. The idea behind the proof of this definition is that if you just take these two terms and add them over, then you get the normal triangle inequality. You just get the normal triangle inequality. After you do maybe a little bit of rewriting and rearranging, you can see that adding these two terms over to the right-hand side gives you the normal triangle inequality. So you can kind of proceed from there. One last thing is that, to summarize some popular metric spaces here that we'll be referencing a little bit later on, and you might see in your homework as well, are these spaces here. And I want you to kind of take a look at these a little bit. These use some of the metrics that we have been looking at. I forgot, unfortunately, a square root here. Put a square root on this d sub 2. There we go. So that makes a little bit more sense. But you can kind of take a look now at these sequences and see how we write through these metric spaces. Kind of the main idea between each of these is that these are all subsets of R infinity. But remember, back from the beginning of today's talk, we said that R infinity does not have some of these things as metrics, because these things are going to give us infinite distances if we choose particular elements inside of R infinity. And remember, those elements that I chose, like 1, 1, 1, so on and so forth, and 0, 0, 0, so on and so forth, that these sequences here would make it so that this distance is infinite between these two sequences. But notice that they do not satisfy the condition of being inside of this little L1 space. Little L1 is the space of summable sequences. It's the sum as I goes from 1 to infinity of the absolute value of the x of I being less than infinity. that is a condition of being inside of this set. Notice that our first sequence here is not inside of that. But if I restrict myself to the subset of all these R infinity spaces such that these sequences are summable, I claim that I don't have to worry about the infinite nature of D sub 1. And the hint there as to why this is a finite function is going to be because of the triangle inequality. And I encourage you to see if you can try to spell out why that is. Notice here we also have L infinity, the space of bounded real sequences in the real numbers. And I claim that this also gives us a finite function, and that is not the case if I remove the word bounded for the D infinity function. We also have C0, this real sequences that converge to 0 with the D infinity metric. I encourage you to take a look at why that works. And then finally, this notion of little l2, which is the space of square summable sequences. Think about the connection between each of these subsets, right? And a little bit of an exercise that's a neat thing to think about here is this. Are any of these subsets of R infinity, are they also subsets of each other? So think about what these two four spaces are. Any of these subsets of R infinity also subsets of each other? Something to encourage you to think about, because that might help us with this notion of, for example, why does C0 get the D infinity metric as does L infinity? So there's a little hint there that there might be some sort of subset relation between the two of these. But that'll do it for me today. We've gone through quite a bit today, getting some examples and some new intuition on metric spaces. Did not want to touch anything else today. Not convergence, not continuity. Leave that for later days, because we've had a lot to go through and kind of dig through just by looking at what these spaces entail, how proofs look different inside of these spaces. So I want to encourage you to take some time and really dig into some of the examples that we've been looking at and some of the ways that we've looked at how to analyze some of these metric spaces. So we've talked about some of those different types of metric spaces: discrete spaces, taxicab geometry, L1, L2, L infinity, all the distance that come from each of those. We've looked at piecewise functions and how to tell distances between functions with each of these metrics as well. The big thing that I want you to take away from this is that there's a lot of metrics on a lot of different spaces, but that the ones that are going to be the most important for us moving forward are D1, D2, and D infinity. Given any metric, though, you can now go through and show that something is a metric given our definition, using the triangle inequality and all of its other conditions. And we can talk about how to show unit balls are different in each of these spaces, especially in terms of things like R2. We finally started talking about functions between metric spaces with terms like isometry and with embedding. But that'll do it for me today. Thank you so much. Have a wonderful day.